Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at the adjoint of a real finite dimensional linear map. So in this topic, we will find the adjoint for real finite dimensional linear maps. That is, we will find the adjoint for real matrices. We will call the adjoint of a real matrix the transpose of the matrix for good reason. We will also consider the relationship between the rank of a matrix and the rank of its transpose. Now, given a real linear map A that maps Rn to Rm, then recall that it is easiest to think of A applied to U or A times U as calculating a linear combination of the columns of the matrix A where the coefficients are the corresponding entries of the vector u. Now, in that case, let's try to figure out what the ith entry of the vector a times u is. Well, the ith entry is going to be the ith entry of each of the corresponding column vectors, each multiplied by the corresponding entry in U. So going back to the matrix, this is going to be the first entry of U times the entry AI1 of the matrix, plus so on and so forth up until the last entry of the vector U times the matrix entry AIN. We can write this more succinctly as the following sum where j goes from 1 to n. Thus, if we can calculate the ith entry of a times u, then we can find the inner product of a times u and v, which is essentially the sum I going from 1 to m of the ith entry of a times u times the ith entry of v. Now, here we have inside the sum the product of a sum and the scalar v sub I. Well, a scalar times a sum is the same as that sum with each term multiplied by that scalar. So I can bring the scalar into the inner sum. All right. Now notice that I now have a sum I going from 1 to m of a sum going from j going from 1 to n of some things. Well, that's the same as summing from j going from 1 to n and then summing from I going from 1 to m. So the term is the same. Now, however, notice that I can rewrite the term of the inner sum to replace or transpose the entries vi and uj. All right, now the outer sum now deals with j, and so u sub j is common for every single term inside the inner sum, so we can take out u sub j. All right, now what do we have here? Well, this just looks a lot like the inner product of the vector u and something multiplied by the vector v. So now we have to simply figure out how do we interpret this jth entry of the adjoint of a multiplied by v. So what is this jth entry of the adjoint times v, which is equal to this sum? Now j here now can go from 1 to n, as the adjoint times v must be n-dimensional, as we're taking an inner product of an n-dimensional vector and the n-dimensional vector u. Well, rewriting it or expanding it, we see that it is this sum here. The first entry of V times the entry A1J, and so on and so forth up until the last entry of V times AMJ. So we're essentially taking a linear combination of all of the entries in a single column of the matrix. Let's go back to matrix vector multiplication. Here we are taking a linear combination of all of the entries in a single row. So consequently, A star times V is a linear combination of the rows of A, as opposed to a linear combination of the columns of A. Thus, it seems that the dimensions of the adjoint of an m by n matrix must be n by m. The ijth entry of the adjoint is the jith entry of A. Or in other words, the ijth entry of the adjoint is AJI. Basically what that means is if this is my matrix A, then the 2, 1 entry of the adjoint is the entry 1, 2 of A. So what does that look like? Well, that looks like this matrix here. This is a 4 by 3 matrix. And so, for example, the entry 3, 1 of the adjoint is 0.8, which is the entry 1, 3 in the original matrix A. Similarly, the entry 4, 3 in the adjoint, negative 5.4, is the entry 3, 4 in the original matrix A. What we have essentially done is we have reflected the matrix through the diagonal. So you will notice that the diagonal entries have not changed. However, the entries negative 5.6 and 7.9 are swapped. The entries 0.1 and 0.8 are swapped. And the entry negative 0.3 is moved down to the corresponding location in the matrix A star. Now, the English word transpose can mean for the position of two objects to be switched. That's essentially what we are doing with these matrices. Hence, for finite-dimensional real matrices, the adjoint is that matrix that has each entry off of the diagonal switched with its mirror image across the diagonal. Hence, for finite-dimensional real matrices, the adjoint will be called the transpose. And instead of having it marked as A star, we mark it as A with a superscript T. However, A superscript T still continues to have all the properties of the complex conjugate, with the exception that the conjugate of a product is the product of the conjugates, whereas the transpose of a product of two matrices is the product in reverse order of the transposes. Consequently, if a theorem, such as the ones we saw in the previous topic, refers to the adjoint of a linear map, if you are applying that theorem to linear maps on finite-dimensional real vector spaces, you may substitute the phrase the transpose. So, for example, the transpose of a matrix is the matrix itself. It is important, however, to remember that the defining feature of the transpose is how it interacts with the inner product. So given a just an arbitrary matrix A times U such that A times U has the same dimension as V, then the inner product of A times U and V is the same as the inner product of U and A transpose times V. Let's check if this is actually true. Here we have a matrix A. It is 3 by 4, so it's mapping a 4-dimensional vector onto R3. Here U is a 4-dimensional vector, so A times U is a 3-dimensional vector. We will take the inner product of that with the vector V. Here is the transpose of A. Now, if we calculate it, we see that A times U is the vector 6, 5, negative 2, and the inner product of this is 12 minus 20 plus 2, which is negative 6. On the other hand, A transpose times V is the vector 0, negative 15, 3. And the inner product of U and A transpose times V is 0 plus 16 minus 30 plus 9, which is again equal to negative 6. Next, our goal is going to be to show that the rank of A is equal to the rank of A transpose. So, to prove this, we're actually going to start with a theorem and then give a sketch of the proof for the above claim. Now, given a collection of vectors u1 through uk in r to the n and a linear map that takes r to the n to r to the m, if the collection of vectors A applied to u1 through A applied through uk in r to the m forms a linearly independent collection of k vectors, then the original k vectors are also linearly independent. Proof. Well, this is a theorem of the form if A, then B. So if A times u1 through A times uk are linearly independent, then u1 through uk are linearly independent. So this is of the form if x, then y. Another way of stating this is if not y, then not x. So if we show that if u1 through uk are not linearly independent, then that automatically shows that, if we can show that, that implies that A times u1 through A times uk is not linearly independent, then we're done. All right, so let's assume that the vectors u1 through uk are not linearly independent. Then there exists a non-zero linear combination of these vectors that equals the zero vector. So what this says is there exist k scalars, alpha 1 through alpha k, not all of which are 0, because of course 0 times each of these vectors added together is the zero vector. But if there is another linear combination where not all the scalars are 0, in that case the vectors u1 through uk do not form a linearly independent set. All right, so if they are not linearly independent, then there exist such scalars. But wait a second. A is a linear map. Consequently, A applied to a linear combination of vectors is that same linear combination of A applied to each of the vectors. But wait a second, the scalars have not changed, and therefore we have just found a linear combination of the vectors a times u1 through a times uk such that that linear combination is equal to the zero vector, even though not all the entries are zero. Oops. Therefore, as a consequence, AU1 through AU sub k cannot be linearly independent. All right, so we showed that not y implies not x, therefore x implies y. Now, here's our theorem. If A maps Rn to Rm, then the rank of A is equal to the rank of A transpose. Now, that seems a little bit suspiciously too easy. After all, the range of A is a subspace of R to the M, and the range of A transpose is a subspace of R to the N. So what guarantees that the dimensions of these two ranges are equal? After all, they are in different spaces altogether. Put another way, suppose you take the matrix A and apply Gaussian elimination to it and find a row equivalent matrix in row echelon form. Then take A transpose, which is going to be n by m, and apply Gaussian elimination to that matrix to find a matrix that is in row echelon form. Is it entirely obvious that both of those matrices in row echelon form will have the same number of non-zero rows? Well, let's go through a sketch of the proof. Let us consider the composition A transpose times A. This is a linear map from Rn to Rn, for A maps Rn to Rm, and then A transpose takes us back to Rn. So A transpose times A is actually a linear operator on R to the n. Okay, if U is in the null space of A, then A transpose times U is also going to be equal to the zero vector, as the image of the zero vector is the zero vector. However, if U is not in the null space of A, then that means A times U is not equal to the zero vector. Now let's consider A transpose times U. Well, I can take the inner product of A transpose times U with U, and then I can bring the first matrix there onto the other side by taking its transpose. But the transpose of the transpose is the matrix itself. And so consequently, the inner product of A transpose times U and U is equal to the 2 norm of AU all squared. So if A times U is not equal to 0, then A transpose times U cannot equal the zero vector. So U is in the null space of A if and only if U is in the null space of the composition A transpose times A. What that says is that the rank of A transpose times A is equal to the rank of A. Okay. If that is true, then let us find a basis for the range of A transpose times A. And that is, of course, going to be a linearly independent subset of R to the n. However, because the basis is in the range of A transpose times A, there must be vectors U1 through UR such that those basis vectors are the images of these vectors U1 through UR. Okay, so now we have A transpose times U1 through A transpose times A times UR forming a basis which is linearly independent. Well, each of these vectors is an image of vectors in V under A transpose. And from the previous theorem, we therefore have that because A transpose times A times U1 through A transpose times A times UR is linearly independent. Therefore, A times U1 through A times UR is also linearly independent, but in R to the M. Consequently, we're guaranteed that the rank of A is greater than or equal to the rank of A transpose. After all, there may be some additional vectors in the range of A. However, now go the other way and consider A times A transpose. In this case, you can show that the rank of A transpose is greater than or equal to the rank of A, and therefore, since we have both inequalities, therefore the two ranks must be equal. Now, comparing the adjoint and the transpose, remember that a linear map, A mapping a vector space on U to a vector space V, is simply a linear map from one vector space into another. The adjoint of that linear map is a linear map that satisfies this equality. Recall that a linear map mapping Rn to Rm can be represented by an M by N matrix. The adjoint of a matrix is the N by M matrix, that is the matrix A reflected through the diagonal, and hence we call it its transpose. So the transpose is the action of reflecting a matrix through the diagonal. It happens that the transpose of a matrix is the adjoint if the matrix is real. If the matrix has complex entries, that is, A maps C to the N to C to the M, we can still calculate the transpose of that matrix, but the transpose is not equal to the adjoint of that complex matrix. That is a topic for the next set of slides. So, following this topic, you now understand that the adjoint of a real matrix is the transpose of that matrix, and that the rank of the matrix equals the rank of its transpose. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!